Yes, we are going all the way back to the beginning of the book, chapter 0.7, the first one, counting principles. Parts of this is going to be similar to what you did in junior high, but you probably didn't do it quite this basic at junior high. So it's kind of taking a little high school nudge to it. So number one, 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box, its number is written down, and the piece of paper is replaced, keyword, in the box. Then a second piece of paper is drawn from the box, and its number is written down. Finally, the two numbers are added together. How many different ways can a sum of 12 be obtained? Okay, counting principles. We are simply counting. So we're going to draw 2 pieces of paper. So the first paper and the second paper. So what are the possibilities? First one could be an 8, and if we want the sum to be 12, the second one would need to be 4. First could be 7. That would make the second one need to be a 5. First could be 6. You replace it, and you draw the 6 out again. Still a possibility. 5 with 7, 4 with 8. And so the answer to the question is there are 5 different ways that we could get a sum of 12. Question 2. Basically the same question, but the 2 pieces of paper are drawn from the box at the same time. So in other words, there is no replacement. How does that change things? Well, it does change things slightly. We could still have one sheet, one sheet of paper have the 8, the other one the 4, like your left hand, right hand type thing for a second. We could still have 7, 5, but since there's only one 6, you can't have the 6, 6. You could still draw the 5 first and then the 7, the 4, and then the 8. So this time there will only be 4 possible ways of getting that sum of 12. Next thing, fundamental counting principle. Again, you probably did this in junior high. How many different pairs of letters from the English alphabet are possible? All right, how many different pairs of letters? So we're looking for a group of 2. So I'm going to put down 2 blanks of letters. Well, how many letters are there? So we have 26 possible letters to choose from for the first blank. How many letters for the second blank? Still 26 letters. And we always multiply. So 26 times 26. I'm cheating. I don't have a calculator, but I do have the answers on a paper in front of me. So 676. Number 4. I like these types of problems. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with 0 or 1. So, within your area code, okay, our area code here is 936. Now, some of you may not even have that, but generally that's our area code is 936. Then, how many digits are left over for the telephone number? There should be 7. So we're going to have 7 blanks. 5, 6. How many choices do we have for the first digit? Okay. Well, it cannot be 0 or 1. So that leaves 8 options. 2, 3, 4, 5, 6, 7, 8, 9. Okay. Are the possible numbers, but that's 8 options. Now, how many choices do we have for the second digit? Well, now 0 and 1 are available. So you have 0 through 9, which would be 10 possible digits. 0 through 9, 10 possible digits. How many possible digits are there for the next one? Still 10. The next digit, still 10 possibilities. 10 possibilities, 10 possibilities, 10 possibilities. And again, we always multiply. So, how many different telephone numbers are possible within a single area code? 8 followed by 3, 6 zeros. So, there are 8 million possibilities. All right, that was page 1. Page 2, permutations. Permutations are an arrangement of objects in a certain order. The number of permutations of n elements is n factorial. So, question number 5. How many ways can 8 different cans of soup be displayed in a row on a shelf? So 8 different cans of soup be displayed in a row on a shelf. So we're going to have 6, 7, 8 blanks. How many choices do we have to go first? There's 8. Well, now that can is there. So now how many choices are there for which can goes second? There's only 7 choices left. Now how many choices do we have for which one goes third? 6 choices. 5 choices. 4, 3, 2, 1. What did we just do if you multiply all those? Shorthand notation, that is simply 8 factorial. All right, now if you punch all that out, you get 40,320. I was looking for something and I'm not finding it, so I'm not going to worry about it at the moment. Okay, in other words, that's what we just said right there. The number of permutations, the way we can order those 8 things would simply be 8 factorial. So that was an example of that first case. Now, next one. Permutations of n elements taken r at a time. Standard notation, you have the p for permutation in front of the base there. They're both subscripts. We have n, and then after the p is r. N is the total number of elements altogether. R is how many of them we want, though. Formula for this is n factorial over n minus r factorial. So find the permutation of 4, choose 4. So based on this formula, it would simply be 4 factorial divided by 4 minus 4 factorial, which would simply be 4 factorial over 0 factorial. And what is 0 factorial? It's just 1. So really this is just 4 times 3 times 2 times 1 divided by 1, which was just 4 factorial, which really means this one is no different than what we just did up here. There's 4 elements and we're putting all 4 of them in order. So we simply get our answer of 24. Now this one though, slightly different. 7 choose 4. So we're going to have 7 factorial divided by 7 minus 4 factorial. In other words, 7 factorial divided by 3 factorial. Needs to move a little bit. Which leaves us with 7 times 6 times 5 times 4 times 3 factorial being divided by 3 factorial. Those go away. And we are just doing this math right here. Let's see. 30 times 28. 28 times 3 is 84 with an extra 0, so 840. Now just to pause on this, I don't want you doing this, but just to go back to our previous stuff for this particular problem. There are 7, think of it as like the previous problem, there are 7 cans, but we only want to put 4 of them on the shelf. Well, if we're only putting 4 of them on the shelf, then there would only be 4 blanks. But how many do we have for the first choice? 7 cans. Now, how many to go second? 6, 5, 4. Notice where we ended up. But with these permutations, I don't want to just necessarily do those blanks. We want to do the formula for our permutations. Numbers get bigger. All right, next question, number 8. 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? So does the order matter? Yes, it matters whether you were first or second or third. So what this tells us, we are looking at, and why, I don't know why this is like this. Let's move this down. I need a lot more room for that. But what we are doing is the permutation of 8 horses, but we want 3 of them, first, second, and third. So according to our formula, it's going to be 8 factorial divided by 8 minus 3 factorial, or 8 factorial divided by 5 factorial, which boils down to 8 times 7 times 6, which is 336. Alrighty. Next idea. Distinguishable permutations. The number of permutations of n objects of which p are alike and q are alike is n factorial for the n objects, but you divide by the repeats. So if there's p alike, you're going to divide by p factorial. If there are q alike, you're going to divide by q factorial. To demonstrate this, number 9. I'm going to go the long way with this, and I picked a very short word, boo, B-O-O, on purpose to limit our options. How many different ways can you arrange the letters in the word boo? All right. What I'm going to do, we have 2 O's. I'm going to make a list, but I'm going to put subscripts to start with. Let's say the first one is O1, the second one is O2. That's one way of doing that. Or I could start with the letter B, and I could have the second O, then the first O. That's all the possibilities with B as the first letter. What if our first O comes first? Now what are the options? Well, it could be B and then the second O, or I could have the second O and then the B. And those are all the options with that first O coming first. Now what about with the second O coming first? Again, it could be B followed by the first O, or it could be the first O followed by the B. Bottom line, how many things did we actually get here? We got 6, which with 3 letters, 3 factorial, should have got a 6s possibility. So that's what we've got. But according to what we just said over here, we want to do n factorial divided by the factorial of those repeats. So what I want to do here, there are 3 letters, So it would be 3 factorial. But because there are repeating letters in that O repeats, and there are 2 O's, we're going to divide by 2 factorial, which gives us 3 times 2 factorial divided by the 2 factorial. Cancels. Our correct answer is 3. Now, coming back over here to the right side, the real letters don't have subscripts. So if I write that without the subscripts, they're both going to be BOO. You're not going to be able to tell the difference. So basically, I've said it twice. I don't need to say it twice, I only say it once. So we're going to throw that one away. Those are the same thing. Throw that one away. Those would be the same thing. Throw that one away. So how many do we actually have? There's just 3. So that's just kind of proving and verifying that this formula over here actually works. Now in this case, how many letters repeated? Just the one letter O repeated. There were 2 of them, but that was the only letter that repeated. So the O would be the P in this formula down here. There's not a Q. It doesn't have to be that. It's just divide by whatever the repeats are, however many of them there are. So there might be more. So looking at number 10 here. How many distinguishable ways can the letters in the word Tennessee be written? Well, first off, Tennessee. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 letters. So it's going to start with 9 factorial divided by. Do we have any repeats? Oh yes, we've got 4 E's. So because of the E's, we're going to divide by 4 factorial. That's like the P in the formula. But there are 2 N's. So we're going to divide by 2 factorial. That's like the Q in the formula. Well, there's also 2 S's. Keep going. Like I said, that's just a generic formula indicating what's going on. You simply divide by whatever the repeats are, however many of them there are. So 4 factorial for the E's, 2 factorial for the N's, 2 factorial for the S's. And now just simply do that arithmetic. So I got 9 times 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial, 2 times 1, and another 2 times 1. Cancel all that out. Do the math. Chances are you're punching that out in a calculator anyway, because this one won't be very easy math. And we end up with an answer of 3,780. All right, those were your distinguishable permutations. Now, slight change. Combinations. An arrangement in which order does not matter. Now, permutations, order matters. Combination, order does not matter. My trick for remembering these things is I think back to when I was a kid, we always had combination locks. Do you have to put those numbers in a particular order, or does it matter? It matters. The order matters. And so the way I remember it is they were apparently misnamed. Yes, they should have called them permutation locks because the order matters. Okay, but anyway, permutation, order matters. Combination, order does not matter. If order does not matter, then you're going to have fewer things. So the trick that helps me remember this part right there, that's the permutation. The combination throws in that extra R factorial. That is the only difference between the 2 formulas. Now, we did combination formula yesterday with the binomial theorem stuff. So you've already kind of seen this. I don't know if it was yesterday or not. But anyway, with the binomial theorem lesson, we were kind of started with these combinations. So you've seen the formula already. But just be careful, don't confuse your permutations with your combinations. So moving forward here with number 11. A standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? All right. Does order matter? You always got to start with that question. Does the order matter? And the answer is no. It doesn't matter whether you pick up the card first or you pick it up fifth, you have that card. So the order does not matter. Because of that, it makes it a combination. There are 52 cards in a deck of cards. You're getting 5 of them for your poker hand. So it's simply the combination of 52 choose 5. So that would be 52 factorial over 52 minus 5 factorial. That right there would be your permutation. But throw in that extra 5 factorial to make it be a combination. So 52 factorial over 47 factorial, 5 factorial. Give myself a little more room. So I've got 52 times 51 times 50 times 49 times 48 times 47 factorial. Ooh, I don't know what I'm writing. Try that again. Still probably reaching for a calculator as you're doing all this stuff because the number is really big. 2,598,960 possible poker hands. And now the last question, number 12. You are forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? Well, again, does order matter? And the answer is no. It doesn't matter if you were picked first or you picked last. You made the team. But we do need to distinguish between boys and girls. So for the girls, well, since order doesn't matter, it's a combination. But for the girls, of the 10 girls, we're choosing 5 of them. For the boys, it's also a combination. Of the 15 boys, we are choosing 7 of them. Every combination of girls could be matched up with every possible combination of boys. So that will also be multiply. So now just do this math. So this one's going to give us 10 factorial over 10 minus 5, which is 5 factorial, times 15 factorial. 15 minus 7 is 8 factorial, 7 factorial. And punch that out, get your answer. And there you have it. That was the intro lesson here for chapter 0.7. So beginning with just your counting principles, permutations, and combinations.